Why does the Earth orbit the Sun? Do you ever wonder why things move the way they do, or what is at the root of motion? From the Earth orbiting the Sun to the throwing of a ball, it is a question that people have asked since the beginning of time. Impetus is the fundamental idea that the motion of a body results from other bodies, not from itself. It's an ancient idea, but one that is continuing to evolve. In the 14th century, a scientist by the name of Jean Bourdin took the idea of impetus further than it was taken by Aristotle and the ancient Greeks. He applied a mathematical equation to it. Impetus is equal to weight multiplied by velocity. Bourdin said, "We do not need angels to push celestial spheres around, that there is a different explanation, a scientific one." The idea that gods are manipulating motion continued for another 300 years, until the period of Sir Isaac Newton. In 1687, Newton published Mathematical Principles of Natural Philosophy. In it, he revised the concept of impetus in what we refer to today as Newton's laws of motion. Newton's first law states that in the absence of external influences, a body experiences no change in its speed nor its direction. Mathematically, the resulting force acting on the body is equal to 0. Newton's second law states that the change in speed and/or direction of a body results from so-called forces from other bodies. Mathematically, the mass of the body multiplied by its acceleration is equal to the forces by the other bodies acting on it. Newton's laws are taught in school, so you may think that this is where the story of impetus ends, but this is where our story really begins. Newton's laws, in fact, raised questions that scientists and non-scientists could never answer. Some of these questions even seemed contrary to common sense. They were strange paradoxes. Let us now consider 3 of these paradoxes. The first one is the paradox of equal and opposite forces. The question is, why is the force by the sun on the earth the same as the force by the earth back on the sun? Does this make sense when the sun is 333,000 times more massive than the earth? Of course, the distance from the earth to the sun and from the sun to the earth are the same, everything else being the same too, except for the different masses of the earth and the sun. Why would the sun exert the same force that the earth exerts back on it? One would think that the force by the sun is much larger than the force by the earth. Let's now consider the second paradox, the paradox of inertial and gravitational mass. Inertial mass is the mass in Newton's second law on the left. Gravitational mass is the mass in Newton's gravitational law on the right. The question is, why is the mass small m in Newton's second law the same as the mass small m in Newton's gravitational law? The masses in the two laws describe different phenomena, so one would expect them to be different. First, consider the mass small m in Newton's second law. It resists change in motion. Now, let's consider the Earth's mass m in the gravitational law. To predict the acceleration of Earth under a gravitational force, set the force in F equals ma to the force in F equals the gravitational constant times big M times little m over distance squared. The Earth's mass cancels and we get acceleration a equals gravitational constant times big M over distance squared. The acceleration of the Earth is independent of its mass. If we were to double the Earth's mass, its acceleration would not be cut in two, it would not even change at all. Inertial mass and gravitational mass describe different behaviors, yet they were set equal to each other. Finally, let's consider the third and last paradox, the paradox of particles and waves. Almost 200 years after Newton published Natural Principles of Philosophy, the field of electromagnetism arose. With this new field, scientists could predict electromagnetic phenomena. And so, by the end of the 19th century, science now rested on 2 theories. Newton's objects were called particles, and Maxwell's objects were called electromagnetic waves. But Newton's particles were not capable of predicting the behavior of Maxwell's electromagnetic waves. It became clear that Newton's particles and his revision of Bourdin's concept of impetus were still missing something. Even Newton himself understood that something was missing. In 1693, in a letter to his colleague Richard Bentley, Newton said that gravity should be innate inherent, and essential to matter so that one body may act upon another at a distance through a vacuum, without the mediation of anything else, by and through which their action and force may be conveyed from one to another. It is to me so great an absurdity that I believe that no man who has in philosophical matters a competent faculty of thinking can ever fall into it. Maxwell would later suggest what Newton was missing. In 1857, Maxwell said to Faraday, "But when we face the great questions about gravitation, does it require time?" In this question, Maxwell was suggesting to Faraday that he might know what was missing in Newton's laws that would unite Newton's particles with his electromagnetic waves. Day to day, we don't hear, feel, or see time. But by adding a time dimension to the 3 dimensions of space, we can create an image of it over time. Our image of Earth orbiting the Sun turns into a space-time image of the Earth spiraling around a time axis. Newton's theory for particles never mentioned the speed of light, or really anything about light, and therefore could not account for electromagnetic waves. Electromagnetism embodied a new idea, the idea that time can serve as a dimension, and by doing so account for waves traveling at the speed of light. In order to resolve the paradoxes that arose in Newton's impetus, we would need to work in space-time. Working in space-time, let's now see how one overcomes the 3 paradoxes and arrives at the modern concept of impetus. In 3-dimensional space, we describe the motion of any point by a position vector, a velocity vector, and an acceleration vector. But in space-time, we describe the motion of a point differently. We describe it by a space-time position vector r, a space-time unit vector e, and a space-time curvature vector k. The space-time position vector r replaces the spatial position vector, the unit vector e replaces the velocity vector, and the curvature vector k replaces the acceleration vector. When the unit vector e is pointing in the direction of time, the point is stationary, its velocity is 0. When it is pointing in another direction, for example, when it is pointing to the right, the point is moving to the right. The unit vector's direction tells us what speed the point is traveling. When the curvature vector k of the space-time path is 0, the point is following a straight line in space-time. The point is moving at a constant speed and a constant direction. With this space-time framework, we can now interpret impetus in space-time. To interpret impetus in space-time, we replace Newton's first 2 laws with 2 space-time change equations. Notice that the first change equation replaces Newton's first law, F equals 0, with P equals 0, where P is a space-time force. The second change equation replaces Newton's second law, F equals ma, with P equals k. Notice that the mass m is missing from the second change equation. Let's go back and see what this all means when we consider the Earth's orbit around the Sun in space-time. In space-time physics, the gravitational force by the Sun on the Earth is the field P equals gravitational constant times big M over the distance squared, and the gravitational force by the Earth back on the Sun is the field P equals the gravitational constant times little m over distance squared. Notice that the force field by the Sun is much stronger than the force field by the Earth, as one would expect. The force fields by the Sun and the Earth are proportional to their masses. However, according to Newton, the gravitational force by the Sun on the Earth and by the Earth back on the Sun are the same. The gravitational force field P in space-time physics is different from Newton's gravitational force F. Let's see how this difference resolves the 3 paradoxes. Let's begin with the first paradox, the paradox of equal and opposite forces. The paradox came from the belief that the magnitude of the force by the Sun on the Earth should have been much larger than the magnitude of the force by the Earth back on the Sun. With the mass of the Sun being so much larger than the mass of the Earth, why wouldn't the Sun produce a much greater force than the Earth? The space-time force field P resolves this paradox. But what happened to Newton's force F? Let's take a closer look at the force fields of the Sun and the Earth and compare them with Newton's force. Notice that F is equal to m multiplied by P. the magnitude of Newton's force is equal to the magnitude of the force field P multiplied by the mass of the point on which the force field acts. Newton's force F by the Sun on the Earth involves the force field P by the Sun and the mass of the Earth. The force field P is an action by the Sun on the Earth, while Newton's force is an interaction between the Sun and the Earth. In other words, we see that P is an action force, and that F is an interaction force. In fact, by multiplying the magnitude of the action force P by the mass m on which the force acts, we obtain the interaction force. The interaction forces between two bodies became equal in magnitude and opposite in direction because we constructed them in this way. Let's now consider the second paradox, the paradox of inertial and gravitational mass. Recall that this paradox arose from the question, why is the mass m in Newton's second law the same as the mass m in his gravitational law? It seems strange because the mass in Newton's second law is responsible for inertia, whereas the mass in the gravitational law is responsible for a body accelerating independent of its mass. These are two opposite phenomena. Was this a cosmic coincidence? The resolution came from realizing that the force F is not an action force by a body, but that it is an interaction force between two bodies. Let's again look at the change equation. The equation P equals K expresses the path derivative of the energy vector of an object. The equation F equals mp expresses that the magnitude of the interaction force F is equal to the mass m of the Earth multiplied by the Sun's force field P acting on the Earth. Let's put K in for P in our interaction force. When the speed of the point is small compared to the speed of light, which is the case with the Earth, we can say that acceleration equals curvature, or A, which equals K. This is precisely Newton's second law. The point is that there really was only one mass to begin, and it corresponded to the intensity of the force field. Space-time physics resolves the mystery of why inertial mass and gravitational mass are the same. It was never a cosmic coincidence. Let's now consider the third and last paradox, the paradox of particles and waves. This paradox was about Newton's particles not being able to handle Maxwell's electromagnetic waves. What was he missing? You may remember that the acceleration of a point is equal to its space-time curvature when its speed is small compared to the speed of light. So, what happens when the speed of a point is close to the speed of light or is equal to the speed of light?
One is predicting the bending of light and the behavior of electromagnetic waves.
Newton's theory of particles merged with Maxwell's theory of electromagnetism. When impetus is described in spacetime by the change equation instead of by Newton's second law, you are now able to predict the bending of light, the behavior of electromagnetic waves, and the orbit of the Earth. With the development of the modern concept of spacetime, we could see that the evolution of impetus did not end with classical science, but would also be critical in uniting particle mechanics and electromagnetism. Only the future will tell what more can be united and what concepts are truly universal.